Good. Okay. Let me start our second seminar. Yeah. The speaker of this seminar is Professor Hajime Fukuda from Tokyo University. He will talk about dark matter search with qubits. Please start when you're ready.
Okay, thank you for introduction. So let me start my talk. I'm Hajime Fukuda from University of Tokyo. And today I'm going to talk about our recent work on the search for dark matter using the superconducting qubit. My talk is based on these three papers, and these papers in collaboration with these people. Actually, three of them, Chen-san, Inada-san, and Nit-san is experimentalists. Actually, they're experimentalists from the high energy group, but they're now working on such kind of quantum qubit stuff. And the other three, including me and Takeo and Tampon, is from the theory group, our group. Okay, so let me start. Okay, so here's the outline of my talk. I will first do an introduction, including the introduction of the superconducting qubit, and then I will talk about our first paper and half of our third paper about the dark matter detection using the one qubit or the separated, not entangled qubit. Actually, we propose to use such a superconducting qubit as a dark matter detector. And we show that we can detect the dark matter whose mass is around the gigahertz. That is the frequency of the qubit. And that corresponds to around 10 to minus 5 electron volt in mass. And in the second half of my talk, I will talk about our second paper about the signal enhancement by using the quantum circuit or entanglement of the qubit. Here, we constructed a quantum circuit to enhance the signal from the dark matter. And I will show the circuit and how the signal is enhanced. And I'll talk also about the quantum noises to the system. And that includes some part of the ongoing work. Okay. And finally, I will introduce the result. Okay, so let me start from the introduction. So first of all, as everyone here hopefully knows, there is a dark matter in the universe, and there are many observational evidences for the dark matter. But the property of the dark matter, but for the gravitational ones, are known. So it is of urgent importance to search for the dark matter in the universe. And in this talk, we have proposed a new method to detect the dark matter using the superconducting qubit as a dark matter detector. So to explain what is a superconducting qubit, but before going to that, I will first start from the question, what is the qubit? So this is also, I guess, almost most of you have heard of, but the qubit is a kind of a fundamental piece of the quantum computation. So it is the artificial two-level system, which consists. Oh, by the way, can you see my cursor?
Yeah, of course, of
Okay,
course.
okay,
We can see you. Yeah.
yeah. So it's the two-level system. Artificial two-level system consists 0 ground state and excited states. And so sometimes people call it kind of like artificial atom because just like a real atom, it's have the ground state and excited state. And by the recent development of the quantum technology, many qubit systems gradually becomes available. And still the noise level of such a quantum system is very high. But we expect that in near future, more and more cleaner quantum system will be available. So the qubit is, as I have talked, it's like a two-level artificial system. But what can be such a two-level system? What can be the candidate of such a two-level system? So there are several types of candidate for such a two-level system are known. For example, photon, helicity of the photon, and or the NMR, or the cold atom, like ion, which is called the ion trap. And the superconducting qubit, and so on. But among the several types of the qubit candidate, one of the most promising one is that this superconducting qubit, which is as known as the transmon qubit, as I have introduced from now. So to explain what is the superconducting qubit, let me start from the easiest example of the quantum system. So of course, it depends on person to person to what is the easiest example of the quantum system. But I guess the one of the obviously easiest example is the harmonic oscillator. So harmonic oscillator is also can be constructed by the very simple physical realization, such as the LC circuit. Here, LC circuit consists of the capacitance and inductance, C and L. Okay, and the energy of such LC circuit is the sum of the capacitance energy and the inductance energy. And by the property of the capacitance, it can be written in this way, so that indeed the Hamiltonian of the system is quadratic, and this is a quantum harmonic oscillator if we quantize the system. And if we quantize the system, we can write down the energy eigenstates. But then let's ask one question. Is it possible to use this harmonic oscillator as a qubit? For example, if we take the ground state as 0 of the qubit and the first excited state as 1 of the qubit, then is it possible to have the qubit in this system? Actually, the answer to this question is no. Harmonic oscillator cannot be the qubit. Why harmonic oscillator cannot be the qubit? It is because the harmonic oscillator is not an isolated two-level system. Well, of course, we know the energy eigenstate of the harmonic oscillator, and that is labeled by the integer n, 0, 1, 2, 3, blah, blah. And the energy eigenvalue of that energy eigenstate are basically proportional to this integer n. So that is the energy difference between energy eigenstates are all the same. Then, for example, let us suppose to take this zeroth ground state and the first excited state as an isolated qubit. And then if we, for example, want to excite from 0 to 1, then basically we have to we have to put some microwave to the LC circuit to excite the ground state to the excited state. And the frequency of such microwave corresponds to the energy difference between zeroth and first energy eigenstate. But then, because energy difference between 1 and 0 is exactly same to the energy difference between 2 and 1, the microwave, which is put in this system, actually also excite the first excited state into the second excited state as well. In other words, we cannot separate this zeroth and first excited states from all the other excited states because all energy difference are the same. So because of this property of the harmonic oscillator, we cannot use the harmonic oscillator simply as a qubit. Of course, to avoid this difficulty, we just need to change the energy difference between each energy level. That is, we just need to introduce the nonlinearity to the system. So how can we introduce nonlinearity to the system? So to introduce nonlinearity, it is known that we can use an element called the Josephson junction. I'm not sure how it's familiar with all audiences. So let me explain the physics of Josephson junction very briefly. The Josephson junction is a junction between two separated superconductor, this blue blue part is supposed to be superconducting. We can separate two superconductors by a thin insulator film. Then, as we have learned in the classes, the superconductor labeled by its macroscopic wave function, which is characterized by the density and the phase. So each superconductors are now, because separated, has their own macroscopic wave function. But as if we make the film thinner and thinner, the wave function at some point start to tunnel to the other superconductor. Then, because of such a overlapping of two wave functions, the current emerges, and that current is proportional to the sign of the phase differences. To see such a dependence, we can write down the Schrödinger equation for the macroscopic wave function. Schrödinger equation consists of the tunneling part and the voltage, impulse voltage part. And we can just solve this equation, and the solution for the I current, that is the time derivative of the number density, and the voltage is written in this way. So indeed, now the relation between the current and the voltage is, except for the time derivative, nonlinear. Or we can see that this relation as kind of a nonlinear inductance relation. To derive the Hamiltonian, we can derive the energy as following. Energy is just a time integration of I times B, so it's indeed nonlinear in terms of theta. So now we can replace the inductance L with the Josephson junction. Now, because the Josephson junction is a junction between the superconductor, all this line part is also the superconducting. But anyway, for such setup, we can now write down Hamiltonian in something like this. Here, V is now proportional to theta dot. Of course, we cannot quantize this system because it's very nonlinear, but in the limit that the nonlinearity is not very large and perturbatively taken into account, we can expand cosine to this form, and we can regard this quadratic part as a free part, and we can assume it's just like a harmonic oscillator with some perturbation. Then the energy level becomes something like this, and because of this perturbation term, the energy difference are all different. And we can separate zeroth ground state and the first ground state as a separated system, and we can use this 0 and 1 as a qubit. And indeed, with some parameter, we can take such a limit, and that system is called a transmon, and that whole system, and then 0 and 1 system is called the transmon qubit or the superconducting qubit. Typically, the energy difference between the zeroth and the first excited states are of order GeV, and later we will see that we can see dark matter whose mass is more or less same as this omega, the energy difference between first and zeroth excited state. And
I have a one question,
yep.
live question.
Yep.
Yeah. In this slide, just in your introduction, just you mentioned about only n equals 0 and n equals 1 state as a
Yep.
quantum qubit.
Yep.
But since all the energy levels have a different energy scale, so maybe I think naively thinking you can use n equals 2 and n equals 3 state as a can be also used as a quantum qubit, not only n equals 1 or n equals 0, right? Yeah.
That's very good point. Yeah, indeed. We can use the higher energy part, higher
Yes.
energy eigenstate, and
Yeah.
indeed some quantum quantum computing people try to use this higher energy to process or to efficiently process the qubit. But the actually one drawback is that as higher the energy is, the kind of more unstable, more the fragile the state is. That is, it's kind of becomes easier to de-excite or easier to lose the kind of quantumness. So in that sense, the use of the higher n qubit state actually not very, in particular, at least just for the dark matter detector, probably because, I mean, we have, as I have introduced later, we have to expose the whole system to the dark matter for some time. But then if the system becomes more fragile, the time is limited. So in that sense, I'm not I don't think it's very advantageous to use the higher excited state as a dark matter detector. But for the qubit manipulation, I completely agree. I mean, that higher energy state could be sometimes useful. Yeah.
I see, I see. Thank you, thank you.
Thank
you
you
so much. Yeah, yeah.
Okay. And then, yeah, one of the big advantage of the superconducting qubit is the actually the ease of the frequency tuning. It's very easy to tune the frequency. Let me show how to tune the frequency. So actually, we can replace the Josephson junction as a loop of Josephson junction. That loop of Josephson junction is called as squid. And the squid is because of the, well, I can explain, but it's a bit complicated. So let me skip the detail. But because of the single valuedness of the macroscopic wave function, the current is the relation between the current and the phase difference can be tuned by the external magnetic field perpendicular to the loop. So in that sense, if we tune the current, because this energy from the Josephson junction is proportional to the current, we can tune this energy difference between zeroth and the first excited state. So basically, we can tune the energy gap by as much as order 1 by using this magnetic field and squid. This is very big advantage compared to the other dark matter detector. Well, still, sorry, I haven't explained how to detect the dark matter, but if we use the system as a dark matter detector, it's a big advantage because, for example, if we use, for example, the cavity as a dark matter detector, then to change the frequency of the cavity, we can do some mechanical stuff like putting some bar inside the cavity and then move bar and then tune the frequency or something. So it's not very easy task. But for the superconducting qubit, we can just change the magnetic flux inside the squid to change the energy gap. So this is one of the big advantages.
What is the out of the conventional magnetic field strength?
Sorry, what?
What would be the typical order of the magnetic field strength?
Typical order.
Yeah, strength of the magnetic field. Yes,
Okay,
yes.
I see. So okay, so here basically this EBS is this phi E. So if we change the EBS, then we can tune this current. So in that sense, if we change this by 2 pi, so it's not magnetic field, but a magnetic flux. So if we change this magnetic flux by the integer amount, then we can tune. So it's of course depends on the size of the qubits. And sorry, I don't have the explicit number now.
Okay, so the easy way is that change the area of the S, right, for the given magnetic field.
Okay, so to see more detail, let me show the some real photo of the qubit. So basically, the qubit is something, some chip printed on, or some kind of some chip printed on the plane. And this is just a Josephson junction, but the loop, the pattern is printed so that there is a loop and that there is a two Josephson junction. And so basically that means that the area, this area of this loop is kind of already fixed by the this print pattern of the qubit. So I mean, basically we need to change the external magnetic field to tune the frequency. Yeah, I mean, sorry, I don't have the
Okay.
number for the magnetic field. Yeah.
No, because the reason that I'm asking, because also for your paper about the axion, also you may apply the audition magnetic field, right? So
Yeah,
I don't know.
yeah. Actually, yeah, it's very subtle point. I will talk about later. Yeah, that's
Okay,
very good point. Yeah, that's actually one of the difficulty for the axion search. And but anyway, so yeah, so before finish this section, this introduction, let me show the qubit photo. Yeah, as I talked, the qubit is some kind of chip, and that is enclosed in the cavity. And that whole cavity is cooled by the refrigerator, and it's manipulated by the microwave. This is the actually real photo, real qubit photo taken by our experiment colleagues. Okay, so then let me move to the our work, the dark matter detection method with the one qubit or separate qubit. So as I have mentioned in the outline, I will basically target the dark photon and the axion as a dark matter. But the dark photon, dark matter is actually more easier. Well, I will mention that point shortly later. So let me start from the dark photon, dark matter, and how it, and let me introduce how it interacts with the standard model particle. Well, that is very easy because the dark photon, dark matter is the massive vector boson with the kinetic mixing with the standard model photon. So if we solve the kinetic mixing, the dark photon field directly couples to the standard model current. So the dark photon, dark matter background looks like an effective electric field background. So well, then the story is very simple. So then how about then the next, another target, the axion dark matter. The axion dark matter is the pseudo-scalar dark matter candidate with the Chern-Simons coupling between the standard model photons. So because of this Chern-Simons coupling, we usually, when we consider the axion dark matter detection, we usually impose the external magnetic field B0. And then with such a background magnetic field, the Chern-Simons coupling works as the source of the electric field if the axion background A exists. And the effective electric field is something like this. But now, actually, that means that if we want to have the effective electric field from the axion, we have to impose strong magnetic field. But as the name superconducting qubit suggests, or as I have explained, in the superconducting qubit, we use the superconducting element, that is a Josephson junction or the qubit. But such a superconducting device are very vulnerable, very weak against the strong magnetic field. Strong magnetic field can break the superconductor. And also, to be worse, the qubit has, as I said, is very sensitive to the magnetic field perpendicular to the loop. So again, this combination is very weak against a strong magnetic field.
One question.
Yep.
Yeah, so in this case, are you considering type 1 or type 2 superconductivity?
Well, sorry, I haven't. I don't know what. Yeah, what kind of the superconductor we use, but
Okay,
yeah.
my question is that this strong magnetic field penetrate into the body of the superconductor or not?
Oh, I mean, I think basically, if the magnetic field is strong enough, there's some critical magnetic field, and above the such critical magnetic field, superconductivity could be broken, basically.
Yes. Okay.
Yeah, but yeah,
Let me ask later. Okay.
yeah. In addition to that, yeah. Anyway, the squid is also very sensitive to the perpendicular magnetic field. So yeah. Anyway, the strong magnetic field is not very compatible to the superconducting qubit. But actually, quite recently, some experimentalists reported that if the magnetic field is parallelly imposed, so this is the fold of the qubit. So if the magnetic field is parallel, so the parallel direction, then they succeeded to impose a strong magnetic field as 1 Tesla on parallelly along to the superconducting qubit. So of course, we agree that it's very challenging. In the result figure, we'll take the strong magnetic field, the magnetic field as 5 Tesla. And we guess probably such value of the magnetic field could be possible to impose in the future. Okay, so then I have now introduced the interaction of dark photon dark matter and the action dark matter. But in both cases, they act as effective electric field. This one. So to consider the interaction between the superconducting qubit and the dark matter, we then need to think about the interaction between the qubit and the electric field. So how does an external electric field excite the transmon superconductor qubit? So superconductor qubit is something like the circuit between the capacitance and the Josephson junction. So if we impose the electric field, the Hamiltonian, the energy of the system is something like the CV times the external voltage, VE. And then V is after quantization, just the canonical variable. So it corresponds to the Pauli X for the qubit. And the E is induced from the dark matter. So eventually combining them, the interaction effect is encoded to this Hamiltonian, and the effect is product of the Pauli X times the oscillating part of the dark matter. And we parameterize the other dependence, including the field strength or the parameter of this superconducting qubit as a parameter eta. And here, nx is the direction of the dark photon, which is random, and alpha is the phase of the dark photon that is also random. So, well, in this example, I have used the dark photon dark matter, but for the case of the action dark matter, the story is also the same. Eventually, the effect of the interaction can be written as the Pauli X times the oscillating part. Okay, then with
Excuse me.
Yep.
So in the previous slide.
Yep.
So for the like a dark photon, the alpha is kind of random. So do you need to integrate out the alpha eventually towards
yeah.
NX?
That's very good point. Yeah. we basically take the average for both nx and alpha in the last. I mean, to calculate the sensitivity.
You mean to
Because,
take the average value instead of the integrating out?
sorry, integrating out and taking average is the same. So
The
I
same.
mean, yeah,
Okay.
I'm not sure. I
For
mean,
example, sine alpha, if we integrate the sine alpha for the full phase
okay.
space, it should be zero,
Integrate.
right?
Okay. I see. Okay, I now understand. Well, the point is that the alpha is constant in the some dark matter block. I mean, for some finite time. So in that sense, for that time, the offset phase is always assumed to be constant. So in that sense, we can just take the average over alpha in the final result.
So some kind of the coherent wind of the dark photon.
Yeah. I mean, yeah. I mean, we assume that the dark photons is dark photon dark matter is coherent over like a Dobroi length of its dark matter, and inside that coherent length, the nx point the same direction, and also the phase is the same. Actually, the phase has nothing to do with for the single qubit, but it later it becomes global, but so I think that average taking the average is enough to ignore to average the effect of the direction and the phase. Okay. So then now the Hamiltonian of the qubit is given by the following way. The Hamiltonian is sum of the power z and the interaction effect. And to solve the system, we just need to move the interaction picture as usual. That is, we take the effect of H0 into the operator, and then we take the effect of the interaction into the state. Then the Schrödinger equation is something like this, where the interaction Hamiltonian is given by this as usual. And to simplify things, we can just calculate this, but there are lots of terms appearing, but we can adopt the approximation, so-called rotating wave approximation. That is, if we calculate HI has not only this slowly rotating term, but also fast rotating term, and also the sine terms. But we just drop such a higher oscillating term and the sine oscillating part. That is basically equivalent to assume that the time scale we consider is much longer than the oscillating scale of such higher frequency modes. And indeed, that approximation will be the case for the dark matter detection. And to simplify more, we just assume that the mass of dark matter is close to the qubit, and also ignore this cosine term. Or in other words, if the dark matter mass is close to the frequency of qubit sufficiently, then we have the sensitivity to such a mass of dark matter. Okay. So, actually, up to this point, I have ignored the effect of alpha. Well, and in reality, the phase of dark matter is unknown. So H can include alpha, as I show in the previous slide. And then if we do the same procedure, interaction Hamiltonian now becomes rather something like this. But this just specifies some direction of the one power matrix. So it's basically the equivalent up to now, equivalent just now. So, okay. Oops. Then with the this interaction Hamiltonian, and the state evolves in this way. It's now very simple algebraic problem. So if we prepare initially the ground state 0, so if we prepare state such like a 1, 0 at the time 0, then we have the first excited state later. That is, the state is evolved to something like this. And if we try to observe 1 at time t, the probability to observe such state, such excited states, is now something like eta squared t squared. If the eta t is small enough, and also t is smaller than the coherent time of the system. Well, yeah, this is also asked by the audiences, but oops. Yeah, the coherence time is something like that determined by the combination of the coherence time of the dark matter and the coherence time of the qubit. Well, coherence of time of the dark matter is, as I have introduced, it's like assuming that the dark matter is uniform inside one blob of size of the de Broglie length. So the time for such dark matter blob to pass corresponds to the such coherence time of the dark matter, coherence time of the dark matter phase, and that is of order 1 over mv squared. And on the other hand, qubit itself has kind of coherence time. That is because qubit is a quantum system, and if we put the quantum system very long, the coherence of the quantum system can be blocked. That can be understood as something like a Q value in the cavity system. For example, in the usual cavity, the Q value is like a 10 to 5, 10 to 6 or something. In some sense, we cannot sum up all the photon inside the cavity for the infinitely long time because of the property of the cavity. And similarly, for the qubit, we cannot accumulate the excitation, this element of the excitation for the infinitely long time. And typically, by the current technology, the Q value is for the qubit is around 10 to 5 to 10 to 6. And the coherent time is in time like 100 microsecond or something like that. And with such a limited time, we can also fix the range of the frequency. So, well, yeah, as I have shown in the previous slide, we ignore the oscillating part of this cosine. That means that this phase of the cosine is much smaller than 1. That is, if we fix the observation time t as tau, if the difference of the frequency, MDM and omega, is much smaller than around 2 pi over tau, then we can rely on this calculation, and we can observe the one first excited state. So yes, so now this is the evolution of the qubit. And with this ingredient, the measurement procedure is now clear. We first need to prepare the qubit, well, as many qubits as we want, for example, NQ qubit, to the ground state, and excite all these qubits to the dark matter for some time. And that time is determined by the coherence time of the dark matter and the qubit. And then after the expulsion, we can now measure the all qubit and to check if there are any first excited states in this NQ qubit. And after repeating this procedure sometime, we then change the frequency of the qubit by tuning the magnetic flux in the squid. We can change the frequency of qubit by the something around this to scan another frequency. Then repeating all these procedure, we can sweep some fixed frequency range of the dark matter. So this is the measurement procedure. And before going to the next part, let me mention the another important effect for the signal. So here, in this measurement procedure, we just tune the frequency of the qubit by this procedure 5. So, and this is one of the big advantage compared to the cavity-based experiment, whose frequency are not very easy to change. But we can actually still use kind of resonance between the cavity and the qubit system to enhance the signal. That is, as the qubit itself was enclosed in such a cavity as this photo shows. So, for example, at the wall of the cavity, because the total electric field is 0 inside the metal wall, so the electric field from the dark matter, field from dark photon or the qubit, dark photon over the axion, actually induce electric field inside the wall, and the electric field inside the wall is cancelled by some of this dark matter part and the induced part. And but the electric field from the dark matter is basically constant in the space. So if we see the inside the cavity, and here, suppose here is a wall, then even inside the cavity, this electric field from the dark matter is constant, just this blue electric field. But on the other hand, because of the property of the cavity, the induced electric field in the cavity must be in the cavity mode. And the cavity mode is not constant inside the cavity, so that the induced electric field, this orange electric field, can be large inside the cavity. Then the total electric field, the qubit field, at the center of the cavity is just a sum of this green arrow, blue electric field, and the orange electric field. And in general, the sum can be much larger than the original electric field from dark matter. So we encode this effect of the cavity resonance as the parameter kappa, and the parameter kappa and the kappa equal 1 corresponds to the non-resonant. I mean, the frequency of the dark matter is completely different from the frequency of the cavity mode. But if the frequency of dark matter is close to the frequency of the cavity mode somewhat, we can include the enhancement effect by this factor kappa. So this is the one of the important remark about the cavity and the frequency. But anyway, this is kind of optional. So the minimal procedure is as we showed like this. So basically, we just need to tune the frequency of the qubit and scan over some range. Okay, so now we have explained the procedure of the measurement. And then let me discuss the second paper of our second paper, that is the enhancement of the signal from dark matter. So far, the probability to observe one was proportional to the eta square tau square, and the tau square is the exposure measurement time. And indeed, this tau square dependence is kind of the quantum nature of the qubit. So we have already accumulated the signal in the direction of the tau. But how about the NQ, the number of qubit? In the previous procedure, as actually I will show now, the total probability is proportional to NQ. But is it possible to have the NQ square dependence for the probability as well? So that is the question. So to see this question more in detail, let me show what happened in such a the individual qubit measurement or the previous qubit measurement procedure I have introduced. So in the previous measurement procedure, as I said, we have prepared NQ independent qubit and expose and prepare all qubit into the ground state 0 and expose it to the dark matter for some time. Then the 0 evolved to the 1 with some probability. And then after some time tau, if we observe 1, then we obtain the state 1 with probability p. And then the probability is same for the all other qubit. Then, in total, the total probability to see at least 1 in some signal is around NQ times each excitation probability P. Well, that is just easy mathematics. But then my previous question is that, is it possible to have the probability which is proportional to the NQ square instead of NQ here? That is, if we find some state psi which consists of NQ qubit, which evolve like psi plus NQ times some perpendicular state from the psi. If such a state psi exists, then if we measure the psi perpendicular, then, oops, I forgot the absolute value square, sorry. But the probability to measure this perpendicular state is now NQ square if the amplitude is already proportional to the NQ. So is it possible to, is there any state psi which has such property? So to see, indeed, actually, it's possible. Let's first focus on each qubit individually. So the interaction Hamiltonian in interaction picture was something like eta times sigma x. So the eigenstate of the interaction Hamiltonian is state plus minus. That is eigenstate of the Pauli matrix sigma x, and the eigenvalue is eta. Then, if we think the direct product of this plus minus state with the NQ qubit, just like a plus, 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 blah, 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 plus, or minus, 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 blah, blah, minus, then if we act the Hamiltonian, interaction Hamiltonian of such a NQ direct product state, the interaction Hamiltonian is just a sum of interaction Hamiltonian of each qubit. So this plus times NQ or minus times NQ states are also the eigenstate of this sum of the interaction Hamiltonian, and the eigenvalue is now proportional to the NQ. So if we measure this NQ, we can have the probability which is proportional to the NQ squared instead. So basically, we need to see the relative phase between plus times NQ and minus times NQ in terms of dark matter evolution. And to see the relative phase, we just need to prepare the superposition state between these plus times NQ and minus times NQ. Then, after...
So, excuse me, so my question is actually belong to here. So for the each qubit, the electric field coming from the dark photon.
Yep.
So like you have the phase alpha, right? So
Uh-huh.
I don't.
Ah,
Okay. So
okay,
yeah,
okay.
alpha. So I don't know whether you can just take the average
Okay.
for
I
these
see, I see, I
multiple
see.
qubits
That's,
because they're different in the
yes, yes. That's very. Thanks. That's very important question. Yeah, we assume that the ONQ qubit are kind of just on the one chip or in the very tiny area, so that basically ONQ qubit are in the same flow, same coherent part of the dark matter. Of course, their place different, and the phase could be dependent on the position, but that dependence is suppressed by the velocity of the dark matter, so we can safely ignore that such a position dependence velocity, and then the total not position dependent phase. Sorry, and if and the offset of the phase alpha is considered to be equal for the ONQ qubit. Does this answer to your question?
Okay, so the alpha will depend on the position at the time.
Uh, I mean the alpha. Okay, okay. I should include the picture, but the other picture is following. I mean the inside some blob of the dark matter of the size of its de Broglie length, the dark matter are coherent. That means the phase, the offset of the phase is the same. But of course, or we can assume the dark matter is a plane wave, and of course, as it is a plane wave, the phase is different by position, but that difference is suppressed by the velocity of the dark matter, so very tiny. So we can basically ignore it. Yeah. Okay. Nice. Yes. So yep. Then yeah. Now we perform the Hamiltonian to this plus state. Then the state evolve in something like this. And then we can decompose this state as plus and minus. And indeed, we have the original state plus the perpendicular state with the amplitude proportional to the NQ. So if we measure the evolved state as this perpendicular state, then the probability to observe such perpendicular state is proportional to NQ squared. And that state, this type of state is actually called as a GSZ state. And it is known in the field of the quantum sensing that such use of the GSZ state can enhance the signal. But for the context of the dark matter, we have first pointed this fact out. Okay, then let me then discuss how to construct this GSZ state and how to measure this GSZ state by this perpendicular state. So actually, this can be done by this quantum circuit, but of course, it's very difficult to see how or why this quantum circuit construct this GSZ state and how this is a measurement, but what this quantum circuit means to measure the state by this. So let me explain it more in detail. So to check that indeed this quantum circuit prepare this GSZ state and measure by GSZ state, it's important to notice the equivalence relation on the gate called the C0 gate. So maybe I should have explained the C0 gate. I should explain the C0 gate first. C0 gate is a kind of unitary evolution between two qubit, and it's something like consists of the control qubit and the target qubit, and the C0 gate performs the NOT gate, namely the X, Pauli X to the second qubit, only when the first qubit is 1. So, for example, if the input is a 0, 0, then because the first qubit, contour qubit is 0, we do not apply the x to the second qubit, so output is 0, 0. And if it's 0, 1, it's just same 0, 1. But if the first qubit is 1, then the second qubit is applied by the Pauli X because the contour qubit is 1. And the target qubit is now flipped to 1. And so for input 1, 0, it gives 1, 1. And similarly, for 1, 1, it gives 1, 0. And for the all superposition of these 0, 0, 0, 1, 1, 0, 1, 1, the result are all the same. So the point is that this C0 gate is equivalent to this gate. Here, the C0 control and target are flipped, and we put additional Adama gate. This H is called Adama gate, and if we perform Adama gate to the 0, it gives plus, and if we perform Adama gate to 1, it gives minus, and H squared to 1. So it is easy to check this is this, but well, it's a bit complicated, and I'm also running out of the time, so let me skip that. Then if I use that equivalence relation, the first half of the circuit can be rewritten as something like this. Because, for example, this C0 is H flipped C0 H, and H flipped C0 and H. But the H is equivalent to 1, nothing. So this Adama gate disappear, and it gives just this H and this H and this flipped C0. Similarly, we can remove all this Adama gate and rewrite the circuit in this way. And with this rewritten form, I can see indeed this first part of the circuit generate the GHZ state. Let me check more in detail. So initially, we have all the ground state. So after the Adama gate, the initial 0, 0 state is mapped into 0, 0 plus the 1, 0 state. And if we perform the C0 gate with contour qubit for only first qubit, 1, 0, 0 plus 1, 0 is moved to 0, 0 plus 1, 1. And similarly, after the second C0, the state for this 3 qubit is 0, 0, 0 plus 1, 1, 1. So after all this C0 gate, the state in the 0, 0, 0, blah, blah, 0 plus 1, 1, 1, blah, blah, 1. Then if we perform all Adama gate just map the 0 to plus and 1 to minus. So indeed, we have the plus times NQ plus minus times NQ. Yeah, it's a bit non-trivial to check the relation. So if you are interested, you can check my slide later. But indeed, we can see that we can prepare this state by this circuit. And importantly, now we are prepare 0, 0, 0, blah, blah, 0 to get plus times NQ plus minus times NQ. But instead, if we put 1, 0, 0, 0, 0, blah, blah, 0, 0, then we get plus times NQ minus times NQ. This can be easily seen because after Adama gate becomes 0 minus 1, 0. So eventually we get 0, 0, 0 minus 1, 1, 1, and then we get the plus times NQ minus times NQ in the final state instead. So then the orange part is also now clear because orange part is just the inverse of the this blue part, except for the first Adama gate, which is irrelevant. So if the state at the T2 is plus times NQ plus minus times NQ, the first qubit is just a 0 because this is just inverse of blue. But on the other hand, if the state at T2 is plus times NQ minus times NQ, the first qubit becomes 1 instead. So if we measure the first qubit, this is equivalent to measure the state at T2 by the plus times NQ plus minus times NQ. Okay. So, okay, then let me briefly discuss the last part of my talk, the quantum noises. So up to this point, we haven't thought anything about the quantum noises. Well, or the noises in general. So, but actually the quantum noises are important in such a sensing, in particular using the such a entangled state, such as a GHZ state. To see the effect of the quantum noises on the entangled state, such as the GHZ state, yeah, let me just explain it in detail. So, in the first example, I mean, in the first half of my talk, I introduced the measurement of the separated system. So we have the NQ separated qubit. Then we measure the system NQ times. Then for each qubit, we obtain the one state by the probability eta squared t squared. And but for each qubit, with this probability, 1 minus exponential minus gamma t, we obtain the errors. So in total, we obtain this amount of errors. So to suppress the errors, we have to take the measurement time t, something around gamma inverse to suppress the error enough. On the other hand, for the entangled system, the system is just a superposition of the NQ qubit. So indeed, it's possible to measure the signal with enhanced probability NQ square, but unfortunately, error is also kind of enhanced. So, well, that can be understood as the following. So for the separated system, even if the one error occurs to the, say qubit 2, error doesn't occur in qubit 1 because all these systems are separated and independent. But for the entangled system, because all qubits are entangled, if the error occurs only in this qubit 2, but it's still the error of the whole system. So in that sense, errors are also enhanced. And if we calculate the error rate, of course, it depends on the what kind of errors, but in general, we will have the dependence of the something like this, 1 over exponential minus n cubed. So to suppress this error, we have to take the t as of order 1 over NQ gamma, and that is NQ times smaller than the measurement time for the separated system. So in that sense, if we put t as a t separated over NQ here, actually NQ dependence completely disappear. And we cannot expect any enhancement in such a existence of such large noises. That has been pointed out in the field of the quantum sensing in almost 30 years ago. And actually, this is a big problem to use such an entangled state as a quantum sensor. For the GHZ state,
sorry, I have a question in the your previous slide.
Yep. Here, this one? Yep.
Yeah, for the entangled state, the error looks like getting smaller when the NQ is getting larger.
So what is becomes smaller?
Yeah, the error.
Error.
Yeah. I think naively thinking it is a little bit weird because whenever we have a large NQ, then error has to be
NQ becomes larger, exponential NQ gamma t becomes smaller.
Yeah.
1 minus 0 becomes 1, so error becomes
I see.
Sorry. I agree. Yeah. Sorry.
So 1 means 100%, right?
Yeah. Sorry. Yeah. The way I I wrote was, sorry, bit confusing.
I see, I see. No, no,
Yeah.
no, this is my confusion. Yeah, thank you.
Yeah, it was confusing.
Thank you.
So, yes. Yeah, indeed, for the GHZ state, actually, GHZ state is strong against some sort of error, but against still fragile to errors. So then, is it impossible to enhance the signal for the dark matter detection? Well, actually, to avoid the this nightmare, there are several ways possible to think, possible to consider. First one, that is actually the assumption of our second paper, that for the dark matter detection, actually the coherence time of the system is not determined only by the coherence time of the qubit. It's just determined by the combination of the coherence time of the dark matter and the qubit. And if the coherence time of the qubit is much longer than the coherence time of the dark matter, then the coherence time of the system is determined by dark matter. And in that case, we still have the NQ enhancement in total. And the second way is a little bit more tricky, but the point is that if we correctly count up for the situations such as the dark matter detection, where we have to scan the frequency range, we still have some gain. Actually, this is based on our ongoing work with specialists in the quantum information, this person. But the point is that if we shorten the measurement time by NQ, okay, indeed the probability is now becomes smaller. So its dependence is NQ zeros. But the point is that as the measurement time is shortened, we can repeat more and more time. So we can repeat NQ times more measurement for one beam. And in addition, if we shorten the measurement time, the frequency width can be also widened. That is the, sorry, in the previous slide, I said that the frequency range, the range of dark matter mass, which is possible to scan by qubit, is determined by the condition that this phase of the cosine is smaller than 1, much smaller than 1. So if we shorten the measurement time NQ, the frequency range, this M dark matter minus omega qubit, is increased by NQ. So the number of beams can be actually reduced by NQ. So in total, we found that the signal or significance can be still enhanced by NQ squared. So at least for the dark matter detection, the use of the GHZ state can be useful. That is our conclusion of the second paper. Okay, so with combining all of them, let me show the result of our work. So first, this is the result for the 1-year measurement for the dark photon in our first paper. So this blue shaded region is the sensitivity for the 1 qubit, and the light blue shaded region is the sensitivity for the 100 separated qubit. And here we assume that the coherence time is somewhat around this, and the error is coming from the readout error. And for the dotted line, at this time we had thought about something like a thermal noise, but now we are thinking this thermal noise doesn't make sense, so we can just ignore this dotted line. But anyway, so this is the 5 sigmas discovery reach, and we show that with use of the superconducting qubit, we can explore the unexplored region. In particular, because we can tune the frequency of the qubit.
Excuse me.
Yep.
So here the thermal noise can have the constraint on the frequency of the microwave. So you cannot neglect, right?
Sorry.
So in the transform qubit, the thermal noise
Yeah,
have
okay, yeah.
the bound,
Yeah.
some bound for the frequency of the microwave injection for the qubit. So
Thermal, sorry, are you asking about
thermal noise means the thermal fluctuation inside the qubit.
Yeah. We think it's the thermal fluctuation of the qubit.
Then this thermal fluctuation or thermal noise have some
actually,
lower bound of the frequency of the microwave.
But in some sense, that this thermal noise is already included by the coherence time of the qubit. I mean, first of all, the qubit is cold enough so that the system is coherent.
Actually, the thermal noise is implemented in the frequency range in your plot, right? This order one.
Sorry, this the dotted line corresponds to the kind of more thermal noise range. So and it's but this undotted region is basically the thermal noise is small enough. So in that sense, it's kind of ignored.
Okay, so in this plot, you don't have the error except this readout error. So
Readout error is assumed to be the significant. And I mean, or in other words, we restrict the measurement time so that the error from the such thermal fluctuation or the error from the thermal de-excitation or decoherence is small enough.
for example, so this is kind of same as this IBM qubit, right? So transform qubit. So you can simulate this experiment with this Qiskit. And I implemented this some basic error implementing the Qiskit. Did you check how much the error and this limit can change in terms of this the qubit error?
Yeah, I think that's also include the readout error. And
not readout, but some like bit flip error or some error on the qubit itself.
Bit flip. I think for this case, the bit flip error is the most important bit flip. Yeah.
Okay. Anyway, this is like a simulation, so without error, except the readout error. Okay.
Yeah, this is just a theoretical expectation. Yeah, only with the readout error. And if this is the result for the action. For the action case, this green shaded region and the light green shaded region is the result for the 1 and 100 separate qubit. Oh, by the way, in this dark photon figure, we didn't include the effect of the GHZ state. But if we include the GHZ state, the this dark blue shaded region is enhanced by the 1 order if we use the GHZ state of the 100 qubit. So, and if this is the action, and this dark green shaded region is 1 qubit, and the light green shaded region is a separate 100 qubit. And well, here we use the 5 Tesla, and to sum up, well, of course, it's again very challenging, but to sum up, enhance the signal, we first make use of the packaging cavity effect. That is, if we also tune the frequency of the cavity, and then we can enhance the signal. And this blue shaded region and the light blue shaded region is separated 1 qubit or 100 qubit with such cavity enhanced effect by 100. So, well, this kappa 100, I mean, cavity enhancement effect by 100 means that the frequency of the dark matter and the frequency of the cavity mode is around percent level close. So of course it's very challenging, but with use of the such packaging cavity effect, we can enhance the signal much more. And then in addition, if we furthermore use the entanglement effect, then the ultimate range of the reach is this orange shaded region. And if we make use of all such enhancement factor, we may reach the QC reaction line. So that is the result. So yeah, thank you for listening.
Thank you for the nice talk. Any questions or comments?
I have a question. Do you have noise feature of this device you used? For example, the qubit noise. For example, data taken for to show the noise feature of the qubits.
Oh, actually, our experiment colleague are still kind of developing the qubit, and well, they have some at the qubit, but still, we didn't perform the experiment yet. So they didn't perform the experiment yet. So the detailed data is not taken. I mean, here we have just assumed theoretically there is a order 0.1% level error at the readout. So I think, yeah, of course, in reality, at least at the first step, the error rate could be more large, could be bigger. And yeah.
Okay. So not yet I mean, even a single qubit you haven't had.
No, yeah.
Okay, thank you.
Then what is the dark gray lesion? Is it already constrained or?
Yeah. It's already constrained. Sorry, I've got the detail, but this light shaded region are like other
expectation or
experiment.
yeah.
I think it's already constrained region, and
by experiment, not expectation.
Yeah.
I see.
So I have a very naive question.
Yep.
So I heard that you have this IBM quantum computer in your university. So then the IBM Eagle system in University of Tokyo, right? Yeah. You have some QPU time, and even though you have any freedom to choose the frequency, but for the default frequency of the IBM, you can use this for the rule out on specific range of the mass, right?
Yeah. That's interesting possibility. I mean, our experimentalist colleague try to do that, but yeah, I haven't heard if they're
because you just need to borrow some QPU time, then you just have set a default qubit, default frequency using the IBM Eagle system, and then rule out some specific range of the mass.
Yeah.
Maybe one particular mass, right?
In principle, yeah, that kind of experiment
curious.
can be, yeah, possible. Yeah.
Not even theorists can do that, right?
Yeah. Yes. Let me see.
You have not tried yet.
Yeah,
okay.
for the at least for the dark photon, yeah, we
yes,
do
yes.
things.
For the dark photon case, yeah. By the way, so basically you can do the similar thing on this ion trap quantum computer, right?
Similar things for like a quantum circuit.
No. Yeah, for not the transform qubit, but the ion qubit.
Yeah. But I think some people, like people in KK, have studied by the dark matter detection by the ion trap types qubit. And
because I heard that this ion trap is like the decoherence time like out of the second or very large.
Yeah, right? It's much larger than the the superconducting qubit. But
Yes.
on the other hand, I also heard that it's the manipulation is like because the superconducting qubit is manipulated by the microwave, so it's much.
But also ion qubit, also they manipulate using the microwave, no?
Yeah, well, yeah, but like if the at least if we want to do like entanglement between the like if we manipulate if we want to impose some the gate between two qubit, I think it's like we have to make that closer and do something and separate or something. So it's I heard it's a bit complicated, but yes, I to be honest, I don't I haven't studied it very well. So yeah,
People in KK try to do. Okay.
or I think the theorist wrote the paper, Kitano-san, and
They are using the ion trap.
yeah, I think so. They are using the ion trap qubit. Yeah.
Okay. Thank you.
Okay, any other questions or comments? If not, let's thank to the speaker again. Thank you very much.
Thank
you very much. Yeah. Personally, your talk was very understandable.
Oh, really? Okay.
Yeah, I learned a lot of things in terms of qubit. Yeah.
I think, yeah, it's kind of interesting, and also yeah, it's if once we learn, it's kind of at least the field theory is more difficult. So
By the way, so if the dark matter is like detectable